Hello guys, I'm Dejan Radić, CTO at DexStar. Today I'm going to talk about privacy-enhancing technologies and blockchain. We're going to go through different use cases in this field and see how different technologies fit the space. So let's start. As an intro, generally, when we're talking about privacy, we're talking about the ability to express yourself selectively. We can think about that as a high-level definition, but what we are actually talking about is the freedom of choice. We have the freedom to choose to whom we are going to share our data or information or anything that is actually important to us. And what we are actually thinking in this space is about the consent to use or reveal personal information, or what's called today personally identifiable information. When we're talking about blockchain in general, we're thinking about the system that enables the distributed integrity protection. We're talking about integrity. We're talking about what's being able to tamper-proofly protect the data in general sense. But when we see security as a whole, we generally have confidentiality, integrity, and availability. Since availability is something that's usually sold in distributed systems or in the clouds or anything that's presented nowadays with high availability systems, usually when we're talking about blockchain, we're talking about integrity, but we are not thinking about confidentiality. And that's the biggest question that comes when we're actually expressing something that has to stay private in this space. So, let's say that in general we have these public chains. Everything is transparent. We're used to actually using blockchain explorers to check transactions. We're actually able to see what's happening on the blockchain side and what's actually being presented in this field. But people have come to the solution of actually having something private by using permission chains. That's not a full level of decentralization, they might argue, because we are having the systems that are controlled only by one authority or by a group. And in general, when we're thinking about public chains, we're thinking about the distributed systems in a peer-to-peer network where every collaborator is actually equal to another in this field. But what about the private data in this field? How can we protect it? And how can we actually use the novel technologies in this field to keep the data private? We are going to talk about 4 different, let's say, most popular privacy-enhancing technologies today, and what their aim is actually is the minimization of data sharing with low influence on functionality. Usually, when thinking about security, we are trading the security with utility, with easiness of use, with performance. Let's say in general that if we want to enhance security, we need to give something on the other side. And that usually comes to the user side as something that is making their lives harder. Not many laws have been presented in this aspect, and it's not that complex from technical aspect to actually create the regulatory compliance systems. But let's say that many companies are enhancing those laws through different terms and conditions, and those terms and conditions are actually presenting the challenges in a more narrow way. And when we're talking also about the audit and the enforcement of these aspects, we want to have the organizations which are on the side of actually checking what's compliant in which aspect and if it actually applies to the terms and conditions. And the final result, or the final, let's say, frontier of everything is the ability to control the data transfers. Now let's jump to the first technology today, and it's called homomorphic encryption. For example, let's say that you have some data that's really important to you and that has a value, and you're thinking about storing that data somewhere. Usually you would choose some kind of third-party provider for data storage, let's say a cloud provider. And usually that data is going to be placed in that cloud provider without actually being able to trust to that provider fully. So what are we going to do? We're going to utilize the plain old system of encryption and encrypt that data and also outsource it to that cloud provider, and that actually reduces the attack surface somebody or the cloud provider has over that data, because we are the ones who are holding the key, and we are the only ones who can decipher that data. But what about the data computation? What about the ability to search the data? How we are going to search the data if it's encrypted in the cloud? We're going to pull it from the cloud, decipher it, and then perform the search. And then we come to the point of actually having the huge performance overhead in that aspect. So cryptographic technique known as homomorphic encryption actually enables us to perform operations on encrypted data. In the picture, we can see the data owner who creates a key pair, but we can think about it in a way of symmetric cryptography. Let's say that can be a single key, or as presented in picture in asymmetric aspect. We have a public key, we have a trusted data storage, we encrypt that data and post it to some kind of untrusted cloud host. If we want to perform some kind of operations on that data using, for example, FHE, known as fully homomorphic encryption, we perform that computation on data and get some kind of encrypted program output. And we are actually the only ones who can actually extract the data, since we are having the private key, and get the decrypted program output in this field. Data, as let's say water, has three aggregate states. It's actually data at rest, data in communication, and data in use. Data at rest and data in communication, when we're thinking about the protection of that data, we're utilizing the plain old encryption. But what this effectively enables us is also to protect the data in use by actually enabling the computation on the data that's actually being protected. And that enables the secure processing, outsourcing of data in different clouds, and actually enables people to have more flexibility while actually gaining a lot on security side. Let's say that not all homomorphically encrypting schemes are actually fully flexible. There are the ones that can only perform, for example, addition and multiplication, like Pi-Lier crypto system, or for example, the most known ones, fully homomorphic encryption schemes, which can perform any arbitrary circuits and gates, communication and computation. The technology that also enables similar aspect in this field are trusted execution environment, where similar aspects have been enabled through the usage of hardware-enabled enclaves on a processor level. So let's say, as an example of this, is that you have a company and you have multiple employees in the company. And those employees are creating some kind of expenses through daily operations. But you don't want them to know between each other who has spent how much money regarding their operations. What can you effectively do is generate the key pair, and you as an accountant, for example, you have the private key. They can do the encryption of their expenses by using the public key, send it to you. You perform the addition of all the expenses and then decipher it with the private key. So you are the only one who knows the cumulative amount of the expenses, and none of them actually can reveal the additional information or extract it from that. So that would be one general example. The other examples also, when it comes to fully homomorphic encryption schemes, are enabling full data outsourcing processing, and in this aspect, more flexibility regarding these operations. Let's jump to the next. Differential privacy. As you might know, there have been some research in the US that when you talk about personally identifiable information, 87% of Americans can be identified through gender, date of birth, and zip code. So that means that we don't even have to know the first and last name of those people. So actually, being able to identify you through using different information is something that's being utilized nowadays in the techniques that are called data inference techniques. Let's say that you have some kind of data set, and you can, for example, publish some kind of derivatives from that data set online. That is actually exposing yourself in a smaller sense, let's say, from the privacy standpoint. If you have multiple research aspects or multiple data derivatives that are being published, you're exposing yourself more and more. And that's the aspect that is called privacy budget. Actually, there are several startups that are working in this field, enabling the data aggregation publication in the field so that we can actually use the privacy budget and enhance the ability for you to control your data. And how is this effectively solved in general sense? Let's start from employee salary example. For example, you have a company, you have 150 employees. You publish the average salary that everybody can see. And new employee comes. You update the average salary on your web page, let's say. Basically, by knowing that you are having 150 people, and after the new one coming is 151, somebody can actually calculate the salary of that new employee. So, how do we solve this issue? We're actually not going to communicate the exact value. We are going to add a bit of noise to it. So actually, when we have a large data set, we add a bit of noise, so a bit of randomness in this field, and we get something that we can actually consider being a secure data source. And for example, if we are using that to publish the aggregate data, as for example, US Census Bureau has done regarding their research 2 years ago, we're actually reducing the surface of somebody knowing more about the individual that has been used to calculate that data set. And when we talk about privacy and publication of general information, we don't want to actually include the information about individuals, and that's the solution what we are trying to achieve. Also, one of the techniques that's, let's say, most interesting to me is multi-party computation. We have data that's distributed over different locations. By actually utilizing different techniques of analysis of that data, we're effectively enabled to get the composite information out of different kinds of data sources so that we can extract additional value. Let's say that we have, for example, different people with different salaries in the company, and we want to calculate the average salary, but without anybody revealing the actual salary of themselves. How can we do it? Actually, everybody can do random number generation from -1,000 to +1,000, add it to his salary and communicate it publicly. When we take all of that information and calculate the average number, that is going to be the actual average salary. Why? Because the information of those random numbers are going to be cancelled out, since we are having the information that is uniformly distributed among the minus 1,000 and 1,000 in the field. So, what's the difference from homomorphic encryption? With homomorphic encryption, we actually had the performance overhead. Here we are having the large communication overhead. So it depends what we are trying to achieve. We are actually, with this aspect, we are actually enabled to extract aggregate information from multiple private data sets. And with private setting intersection techniques, also the ability to join different tables, let's say in a SQL manner, we can actually extract really valuable information. And what we are trying to achieve finally is the ability to create a data-driven economy. And by taking, let's say, well-known tokenomics techniques, we can effectively enable people to sell their data and publish it in a general blockchain distributed sense. Now let's jump to zero-knowledge proofs, what's known as most popular, let's say, technique used nowadays in privacy-enhancing world. And we can talk about, for example, anonymous transactions. We are having public chains. Those public chains actually contain a lot of pseudo-anonymous data. That pseudo-anonymous data is actually being used to track the transactions coming from the address A to address B. But how to actually mimic that information, how to actually hide the source and destination of the funds sent. So we are having these, let's say, solutions like Tornado Cash, for example. When we come from one side to Tornado Cash, we post some information and send some kind of funds. We wait a bit, come from the other side with the other address, and actually we are able to perform the transaction and extract that value on the other side without being able to connect it with the input transaction. So zero-knowledge proofs are actually the solution that provides us that kind of functionality. How it works. We have a trusted third party, and we have, for example, prover and verifier. Trusted third party gives some kind of private data to the prover. And with zero-knowledge proofs, we are able to actually prove that we possess some kind of information without actually revealing it. So verifier actually gets the proof that the prover has some kind of information, but the prover hasn't leaked any kind of underlying information that would reveal something that would be valuable to either verifier or somebody who is in the system. One of the examples would also be the authentication, how to prove somebody that we know the password to enter some system without actually revealing the password. So, to conclude, we have ubiquitous and transparent public chains. Those public chains can be checked by using block explorers. We can see all the data that is on the chain, we can actually analyze it and extract additional information. But let's say that we are having a lot of use cases where, for example, people have spent a lot of resources, like, let's say, Earth observation data, to extract that data. For example, you need to deploy satellites in order to get some kind of raster images of the Earth. And by deploying it, you have spent a lot of resources. And you want to have the ability to actually use that data or to sell it to somebody who is going to utilize it. But sometimes you want to give him kind of information that is derivative of that data without actually revealing the data, what is known as a copy problem. So we don't want somebody to copy our data, but we want to give him value from that data. And with the techniques like homomorphic encryption and multi-party computation, we are effectively enabling the outsourcing of computation, and we are enabling the data ownership in this aspect. So that means that somebody can have the data without actually revealing full information about that data, or publishing partial aspects or data derivatives in the field, and using that data to communicate with some other data providers to extract additional value from holistic data. And what's the general conclusion in the field is that blockchain enables us to publicly publish the data, and everybody can have a consensus regarding that data. That means that we are having integrity protection. But by utilizing the mentioned techniques like homomorphic encryption, we can effectively have the data stored somewhere in a private location and use it in data computations to extract additional value. And that has brought us to the point of having the enhanced anonymity and actually more compliance to the laws. Regarding GDPR, that is most known here in the EU, actually we are having the ability to anonymize and pseudonymize data and keep it private in that aspect. But as you know, there are many techniques where you can actually leak a lot of information by just anonymizing it or using some kind of randomly generated identifiers, and those identifiers are not revealing the information at first, but by utilizing the above-mentioned data inference techniques, somebody can actually extract more value out of it, even though it doesn't look at first in that way. So, what would be the new GDPR? It would be more oriented towards the privacy of users in a way that we are not just going to think about pseudonymization and anonymization, but also about the data derivatives that come from that data. And the next deal would be the introduction of these 4 technologies along with some other that are also bringing the value in the system. That's basically it. Are there some questions?
Great presentation, thank you for that. I have a bunch of questions, but I'll resume just for 2 of them. So first one, homomorphic encryption, it's non-interactive mostly, and the other one, MPC, it's more interactive. They both have those issues, like MPC has high communication. How you can see, so what's your opinion about the technology fits in the blockchain ecosystem? And the second one is, so blockchain is a very adversarial environment because of the MEV and the transparency. From my knowledge, fully homomorphic encryption does not yet have this kind of approach. Only MPC has. How you can, do you see any future, like for FHE, to have that in near future?
Okay, regarding the first question, let's say that for the blockchain side, actually, we are really acquainted with the ability to actually create token-based economies with Web3 and all the innovations in the field. So the ability to actually connect what we currently have with some kind of value that is also being kept private is something where we are actually having the use case. That would be, let's say, the general aspect of it. Regarding the second question, let's say that we are having the private information, and we are having multi-party computation system. It produces a lot of overhead regarding communication, and you need to know all the participants in the field, and at this point it's actually possible to do different kinds of calculations. But with homomorphic encryption, for example, fully homomorphic encryption schemes, they are roughly 50,000 times slower than general plain text data computation. So there are several consortia companies that are working on this solution right now, including the blue chip companies. They are trying to actually implement it in a way to be faster with bootstrapping and some kind of innovations in the field, but it's still really slow, and with that kind of performance overhead, we are having actually a really narrow focus regarding the use cases. Right now, I think the biggest advancement in next years is going to be in the multi-party computation space, but with homomorphic encryption, I expect it maybe in a decade roughly.
Thanks, great.
Thank you, Dan, for the amazing overview. I have a question. If we set aside federated machine learning, if we set aside Web3 as some of the major applications for such four technologies, what would you say, which industry is the major driver of advancements in this field and first real applications?
So when you're thinking about industry, you're thinking about the focus, for example, from, let's say, pharmacy or healthcare, let's say. Okay, so in that field, I would say healthcare data, because it's really valuable. Why? From one side, you're having some kind of information that's being used to produce new medication. But from the other side, let's say you're having people who are really concerned about their privacy. Why? People have insurance. And if your insurance house knows that you have cancer, they are going to really rip you off regarding your policies. But for example, if they don't know that, and that's a means of your communication with the healthcare provider, or let's say, if we are thinking about the regional aspect, that's your communication with the state. And we are thinking also about the aspect, does the state think about our data? And healthcare information is something people are getting more and more concerned lately. So I would say that the biggest driver is actually healthcare.
Thank you.
More questions? That's it. Thank you very much.
Wait. Yeah. One more question.
One more, okay.
Oh, sorry. In your view, what do you think is the time period that we should wait for some of these technologies to reach like a common adoption? Because currently they're just operating in some narrow use cases.
Well, regarding zero-knowledge proofs, we already have use cases, and they are, let's say, pretty common. With ZK rollups, with L2 scaling solutions, for example, and anonymous transactions, we are having the full adoption right now. Maybe only a small percentage of people who are in Web3 actually understand how it works and are actually utilizing it, but it works. Regarding homomorphic encryption, at this point it's used in several use cases that are pretty simple. Almost all are in, let's say, proof of concept phase. Regarding multi-party computation, there are more use cases in general, and regarding differential privacy, I think in the last 3 to 4 years we have seen some use cases, but I see it as the next, let's say, step in privacy enhancing in the next 2 to 3 years, apart from zero-knowledge proofs. So as the last resource, I see actually the homomorphic encryption as the last question was. So that's it.
Okay.
Yeah.
Can you?
I wasn't raising my hand, I was scratching my head.
Oh. Sorry.
Okay, no more questions. Okay, that's it for today. Thank you very much for your attention, and see you around.